This meeting is being recorded.
Okay, welcome to GOAT seminar. Our today's speaker is Pavel Hrabák, and he will speak about modeling pedestrian flow.
Okay, thank you for the introduction. I'm very grateful for being given the opportunity to talk here at this seminar. And I will talk about my last 10 years research on agents heterogeneity in cellular models of pedestrian flow. So at the very beginning, I want to apologize that I didn't have intellectual power to prepare a full presentation. So I will be switching between some older presentations and some explanations and demonstrations to show you what the main results of this research were in our group. Okay, so I will start a bit from the history of cellular models of pedestrian dynamics. This may start with the game of life, which is von Neumann's cellular automaton. He proposed the von Neumann has proposed the rules for cellular automaton years before any cellular automaton has been constructed in 40s. And there are 4 rules under which a cell in a 2-dimensional array becomes alive or dead in the next updating step. And several simulations show that just those simple rules are able to reproduce some phenomena of self-reproducing features and collective phenomena. So just we'll try to make an demonstration. Okay. Okay, it seems this is, oh, never mind. So you can see half of the figure. You can see some evolution of this game of life. It usually stabilizes, having there some oscillators, etc. And there have been discovered some patterns, usually having, for some reason, like warfare terminology as glider and warships, etc. So this was okay. Try to
Maybe to maximization.
Okay, maybe maximizing. Cool. Okay, so it was apparently that I didn't change it before switching from monitors, etc. Okay, so this was like the idea of the first idea of cellular automata to reproduce some collective life-like phenomena. Then another cellular automata, which is considered to be a traffic flow cellular automata, is the rule 184 of Wolfram cellular automata of first class. It is a one-dimensional cellular automata being defined in a one-dimensional grid, again with a cell either dead or alive or 0 or 1. And the idea is that the rule that the change of the state of the cell at the position I is given by the transition rules are given by the state of its neighborhood. It's one cell neighborhood, and there are several rules. You can imagine that, okay, the state can be coded in 3 bits. Each bit has a transition rule to the cell in the middle. Rule 184 does following things. If there is 1 and there is a 0 before 1, then the 1 hops to the next position. If there is 1 before this 1, the 1 stays at the point. And if there is a 0 and in front of 0 there is 1, and this 1 hops to the 0.
That's the first one, no?
Yeah, it seems to be like the first one. However, I am changing the state of the middle cell, which changes its state based on the surroundings. Okay, so this if the middle cell has a state 0 and it switches to 1 if there is one in front of it, and because of this rule, which is the same, this 1 becomes 0. So you can see that this pretty much codes a move of a particle on the grid from left to right, and this move is blocked by another particle sitting in this place. So this is rule 184. Here you can see some time-space diagrams of this rule. So at the here at the y-axis we have the state of the cells, and time evolution goes down. And this model has been considered, or is considered, as the very basic, the simplest model of traffic flow. And here you can see 3 traffic modes. The upper one is a free flow. That means there are no interactions and the particles are moving with their maximum velocity, so to say. In the middle, there is somewhat a transition, and that means there are some particles moving in a free flow, but there are some small jams which stop the flow. So here, this black line, which is going back, that's pretty much a block of particles not interrupted by a hole, which propagates backwards. That means against the direction of the particles. And here, the last one is a high density regime where you pretty much don't have, or you have a rare free flow particles and jams propagating backwards. So here we have, even using extremely simple rules, some kind of collective phenomena corresponding to traffic flow. Of course, this is way too simple. What is then used in some simulations as a traffic flow model is like a probabilistic model defined in a similar way, which is called totally asymmetric simple exclusion process. The abbreviation is TASEP, T-A-S-E-P. Exclusion process, I will try to explain the name. Exclusion process is pretty much what is given here in this rule, that a particle cannot hop forward if there is a particle in front of it. The totally asymmetric is referring to a random walk, because at the very beginning of this process, there was a random walk. means you have a particle on the grid which hops with a certain probability to the right, with certain probability to the left, and with a complementary probability stays at its very position. And once the random walk is totally asymmetric, then it hops only to the right or stays at its position. It is probabilistic, and it is a well, or the most investigated random process. Random walks are very popular. And total asymmetric simple exclusion process is pretty much a bunch of interacting random walks where the interaction is provided or performed using the exclusion rule. So I have those random walks. And here is where, like, the computer science investigating these cellular automata and their properties meets statistical physics, because the exclusion process from random walks is pretty much a point of statistical process or stochastic process, which is investigated by statistical physics, finding some stationary properties and Lyapunov exponents, etc. And this has been thoroughly investigated through some phase transitions, and even such a simple process is able to mimic some phenomena as traffic jam occurrence, phantom traffic jams, etc. Okay. Phantom traffic jam is something you maybe don't know the term, but it is definitely something you know. It is a situation where you are driving on a highway and there is a jam, and then the jam ends and you can find the purpose or the reason, and the reason seems to be like overreacting of people on the highway and imperfect reaction to the previous cars, etc. And of course, cellular automata were in investigating to mimic such reproduction of this situation. There's a funny story. There were some experiments in Japan where they put about 30 cars on a ring and told the drivers to drive at a constant speed of 30 kilometers. They started with a uniform distribution of the cars, and within a few minutes there was a traffic jam on this ring happening. Okay, so these aren't pedestrians; these are cars. So it was quite natural to like expand this process to 2 dimensions, and the most direct expansion is the Floorfilled Model, which appeared in 90s somehow. In 2 dimensions, you have a problem that you don't have a given direction in which the particles to move and to interact. So this has been replaced by a Floor field, which is here indicated by the color. I wanted to say the darker the color, but the more red the color is, the lower is the potential of given cell. So like particles are attracted to the cells with lower potential, as in classical physical system. And the dynamics is again defined by hopping probabilities, by the probability of a particle to hop with now the neighborhood is not like 2 cells in front and in the rear, but pretty much a neighborhood in the distant one in this 2-dimensional dimensional grid. So there are pretty much 2 kind of neighborhoods. So once I have here the particle in the middle, I can use all 9 cells, means 8 cells neighboring and the cells itself as a Morse neighborhood. I can use only the rectangular neighborhood, which is von Neumann's neighborhood. And now it is still called a cellular automaton because it can be transformed to a cellular automaton. However, now the rules are not translated into the rules of how the cell state changes, but rather we are considering here the particles sitting in the grid, and based on its neighborhood, the particle moves to some target position. So there's a switch to like target particle-oriented definition of the motion. The particles are moving probabilistically, with the probability being somehow reflecting here the potential by the static field. And of course, the particles are interacting between each other using the exclusion rule mainly. So you cannot enter a place where another particle sits. Okay, so just to show you again some illustration. Yeah, sure. Okay, so this is on the backwards. This is the task set, the asymmetric simple exclusion process. It is a process with simple interactions. You start to braking once you bump in the previous car's bumper. So okay, but I wanted to show you. Come on. See, I'm well prepared for the shows. Huh? I apologize for being slow, but I have problems manipulating the mouse. So this is an example of the simulation where you can see a random motion of the particles. It should end with an evacuation. It did not for some error. So that's the very principle of this cellular automaton. There are some concepts which I will be talking a bit in detail later, but usually these models are using in parallel update. It means all particles update parallelly. And here you can imagine that once you have two particles, like listening to the exclusion rule, they can both choose the same cell, which is called a conflict. And there is a necessity to solve it somehow. And the guys who invented this, or came up with this Floorfilled model, have introduced the concept of friction. That means once such a conflict occurs with a certain probability mu, nothing happens. And with the complementary probability, one of the conflicting particles is chosen at random to become there. And it has somehow been shown that this essence is extremely important for modeling pedestrian flow, because you don't want to, this is what I maybe should have said at the very beginning, we are not trying to develop an algorithm of pedestrians to evacuate as fast as possible. The idea is to mimic the evacuation process with all the faults we do during evacuation. And the concept of friction appears to be very important effect, which blocks the motion usually at the bottlenecks. With the friction parameter, it is sometimes interpreted as like politeness. Okay, the higher the friction is, the more the people are willing to, give the place to the others, so no one takes the opportunity. It is sometimes interpreted as aggressiveness of people. That means once two people are trying to aggressively reach one place, then okay, it again stops moving, or not stops, but blocks for a while. And there actually has been some experiments with soldiers, actually, because it is somewhat problematic to do evacuation experiments with ordinary people when you want to like emulate the panic situation. And the soldiers have been told to, cooperate on a certain level of cooperance, and it has been somehow shown, even using this model, that somewhere in the middle, in the level of cooperation, the evacuation time was the closest. So once the soldiers are too polite and letting other people to go, it hinders the evacuation. In the same way, once they are trying to aggressively reach, regardless to others. Okay, so this was the state of the art before I came to this topic. And we started to work on it with Marek Bukaček, and we did it for almost 10 years. Well, how did it happen? Actually, I was studying the total asymmetric simple exclusion process, finding its stationary time headway distribution. And Marek came to me and said to me that he will be my bachelor student doing the two-dimensional expansion of the total asymmetric simple exclusion process. Like, it was his idea, and it was his idea to be my student, and it kind of happened to me. Now, regarding the cellular automata for crowd evacuation, I just want to show you here that there is a review article 3 years old, where it tried to review all possible cellular models, okay, from a lot of views. And here you can see that there is quite a large table of possible models and concepts developed for cellular models, because the cellular models have one big advantage, that you can come to it, think of your own rule, do the simulations, and saying, okay, in this very simple single aspect, my model is better than the others. And all of people do that, and well, I did it as well. And then I found that it's pretty much not the way. So I tried to a bit investigate the properties of the existing models and try to calibrate it a little bit. And this is the main, main part of the talk. So I will switch to a presentation, actually from a year 2015, where we have proposed our new best model ever to be done, which has been somehow leaned over the experiments we did with students at Faculty of Nuclear Sciences and Physical Engineering. So here's some experimental setup. We tried the students to walk to the room with a given inflow rate, and their idea was to get through the room as fast as possible and join the crowd at the very beginning over here and enter again. And we tried to simulate the panic-like situation by that, because usually once you have 30 people in the room and you don't want to be very offensive, you just wait before the others leave and then leave at the end. This cannot happen once they are new students going there. So this was a bit emergency situation. And what we did was a measuring of a travel time of a given pedestrian. That means a time which takes the very pedestrian from the entrance to the exit of the room. And this was like the quantity. We had 75 students which were able to create a crowd of 50 students trying to reach a door of the width of 60 centimeters. And when we did the first, let's say, evaluation, we have found out that there were even negative velocities, measuring the velocities like towards the exit. And we thought that it was a mistake. So we found the very moment in the video, and we found out that some small and fragile girl decided not to be part of this experiment any longer, and just went backwards to avoid like the pushing and such like that. So okay, just the piece we tried to evaluate the videos semi-automatically, so using some image recognition with then some corrections. And what is important, every pedestrian had a head with a binary code on it. So we could identify these the pedestrians, which enabled us to group together the trajectories of a given pedestrian. So we are, as I said, we are investigating the travel time, and here you can see a plot of the travel time through the room in seconds, depending on the average occupation of the room throughout the trajectory. And we have discovered like such patterns. And here you can see a green guy who has quite low travel time despite high occupancy in the room, and the red guy who has pretty much linearly increasing travel time with the occupancy of the room. That means, based on this crowd, we can somehow identify people as like those aggressive ones who are pushing through the crowd and are able to reach the exit sooner than the others, and those slow ones who are not really willing to, play this game according to our rules. So this was our idea, and we were thinking how to, capture this by cellular model. So we are trying to modify the Floorfilled model, and okay, so to explain it, just the main contributions what we came up. One of it was a principle of bonds, which says that, okay, usually when you have the classical Floorfilled model, then the target cell is chosen from the unoccupied ones. It's quite logical once you want to keep the exclusion process. However, we thought that it might be useful to let the agents, I will not call the particles agents because they have their own methods, etc., to choose even the occupied side, because it can get empty during this one step. So the idea was that, okay, some agents can choose even from the occupied cell. So if the most attractive cell is occupied, the agent creates a bond to it and waits before it becomes empty within next step. So you can imagine that there can be like a tree of several trees of bonds in the crowd. So once the closest agent moves, then the others can move as well. But of course, there can be some forks. It means there is a conflict solution even with the forks, etc. So this is an idea how we tried to model like the line formation, which is apparent in pedestrian dynamics. once you are not in a hurry and you don't want to, be aggressive towards the others, the best strategy is to stay behind someone who is aggressive and follow him. Okay, so this is what we tried to model, and we tried to model some velocity related aspects, which then have shown to be like negligible and not having for impact. So I won't talk into it into too much detail. And what we introduced next was a dedicated property of those engines, dedicated parameter, which we called aggressiveness. And the idea was that everybody is carrying his aggressiveness, and once once there is a conflict, then pretty much the more aggressive agents prevail the conflict, the less aggressive are excluded from the conflict, and there is pretty much only a conflict between those most aggressive ones. So, okay, it was an idea. Later on, we have changed the decision process a little bit. So the probability of being chosen in a conflict was proportional to the aggressiveness, which came up a better way. And what we tried to model was whether we can capture, using this aggressiveness and bonds concept, what we saw in the experiment. It means people that were able to push through quite fast and people who were standing there. And we believe that we are quite successful about it. So here we can see some comparison between aggressive agents and slow agents. So there we have slow aggressive and fast aggressive, etc. So the travel time of the few aggressive of the low aggressive agents was much higher than those who were more aggressive, of course. However, we try to even capture this velocity. So here you can see that aggressive agents with low velocity, aggressive agents with low velocity, this blue one, can reach the travel time similarly to those aggressive with low velocity. Well, with high velocity. So, okay, now I'm a bit confused. I confused myself a bit. So we thought we are able to manage such a behavior, and just to show you some videos, it is here. So this is a video from the experiment. So at the very beginning, there was an empty room, and we let people entering there at given flow rate. That means there was a signaling device which signaled the people to come in, and we have investigated this transition from the free flow phase to such a cluster formation and a jammed phase, which has been characterized by the size of the cluster. The very jammed phase was characterized by the growing cluster. Further, here's some detail when you can observe some aggressive behavior, some people pushing through, some of them waiting. And there should be some guy going back, but I can't see it right here. But we have noticed, observing this experiment, that, okay, here is cellular model by which we try to capture the phenomena there. We found out that the ability to push fast through the crowd is not given only by the aggressiveness, by the ability to win conflicts. You might have noticed that there are some people like going around the crowd, which was a very effective strategy, of course. So, okay, we thought whether this can be captured as well. Okay, so we ended the video. And we did the further analysis. Now I will do something I hate when it's being done. It's, you know, showing paper in the presentation. But this has not been presented yet. We have measured. Hey, come. We've analyzed the trajectories. You can see a graph. At the x-axis, there is a number of pedestrians in the crowd, the average number of pedestrians in the crowd, and the y-axis shows an angle under which the pedestrian came to the crowd, attached himself to the crowd. And the color here indicates the travel time. So as suggested, the travel time increases with increasing number of pedestrians, of course. But you can see here some blue spots, even in the highly occupied area, etc. And you can see that, you know, like this matter here becomes wider and wider towards the minus pi half and pi half decrease. So because we had the data.
Is it symmetric with the left and right? Or?
No, it's not. It's not. I won't go much detail here, but we have investigated even the density of the trajectories. It seems that the right part was like more dense, because going to the right is somehow like in our minds so heavily, given that the crowd was a little biased to the right. Okay, so we have been able to even identify these spots for individual pedestrians. So this is the same graph, but for single pedestrian. So we have somehow classified the strategy of those pedestrians. This is pedestrians going straight forward towards the exit and not very successful in pushing. This is someone who is trying to bypass the crowd and not very successful at it. And this is a guy who is very successful in bypassing the crowd. And there were other strategies over there. There have been even people who were successful when pushing through the crowd directly. Okay. So what we did was an attempt to describe this by means of the parameters. We have neglected the heterogeneity in velocity, because in the cellular models, which have stochastic nature, it didn't play an important role. But we have defined, like at the very end, 4 kinds of pedestrians: those who were aggressive and try to bypass, those who were aggressive and try to push, and the same for 2 non-aggressive kinds. Distributed them at the very beginning, like uniformly, those 4 kinds of people, and we were able to capture these strategies even in the like travel time diagram and its dependence on the occupation. Okay, that means here the red ones are those who are aggressive and very sensitive to occupation. That means trying to bypass those violet ones are aggressive but trying to push through, means trying to go through the crowd, and then non-aggressive, which are trying to bypass, and non-aggressive, which are trying to, well, not push through the crowd but follow the crowd. So this travel time investigation gave us some idea that this might work around here. And which I don't have prepared for a presentation. Here found out that pretty much these two strategies can be quantified by some sensitivity parameters, and pretty much the strategy chosen is a mixture of probabilistic mixture of two strategies. And it shows that once you have, well, the conclusions of what I'm talking about here is once you have heterogeneity in the crowd, that means, you know, heterogeneity in the parameters, you get completely different results regarding evacuation time. Then once you have like a common parameter for all agents the same, which is somewhere in the middle. So even despite, I don't know, the average flow and other characteristics and average travel time are the same, then in the evacuation time, once you have the heterogeneity in the crowd, the travel time becomes, the evacuation time becomes longer, because you have like those less aggressive agents waiting there or being weighted, so to say. So by this, we try to demonstrate the importance of like this heterogeneity in the decision process, not only in some velocity or size, etc. And there was some work following on our proposal where the aggressiveness was rather interpreted as ability to push through the crowd. And there is a school of researchers, how to say, or people who are trying to do something like that. However, the aggressiveness is in their papers not given like the property of the pedestrian, but it is somehow changed according to the pedestrian's experience. So losing conflicts makes you less like patient and more aggressive, etc. But pretty much the dynamics of the conflict solution pretty much copies this kind of aspect of aggressiveness at the very beginning. Okay, so this is few hardly understandable pictures and graphs supported by nice videos of people trying to aggress. About the future work, I'm like developing this now, is that I've discovered a tool of sensitivity analysis. Means a sensitivity analysis of parameters, how the measurable quantities I'm interested in are sensitive to a variance of given parameters. And we are trying to investigate those models and the experiments just to get the idea how carefully we need to calibrate given parameter and given value of the parameter with respect to the result, the measurable quantities. Okay, so that's all from my side. And of course, if you have any questions or comments.
That's first thing. So questions.
So at least the chairman should have one.
I had one.
Was someone hurt during the?
Of course not.
Especially not animals.
especially academic and students.
What I was wondering about is, it can't be seen from your picture that there is always like also this, because it's the same pedestrian experiencing the same situation. You can also learn from like the mistake. Like
Sure.
I was trying to push through and it didn't work out, so I will try from right the next time. Oh, that's bad, so I will try from left side.
Yeah, this learning effect cannot be like taken away. It's always present once you do some experimental evacuations. And however, we were not able to observe some kind of pattern over about it. Of course, we have more data for those aggressive pedestrians because they were running around and around. And we have done about 6 experiments of this kind with different scenarios. And of course, the results are quite biased by the, let's say, composition of the crowd. Because in some years we had a very enthusiastic student who took it very seriously and were able to emulate quite like emergency feeling for the others. I went to the crowd twice and refused to do it more times. And just, you know, for the imagination, once modeling this solar automata for pedestrian dynamics, you usually use a 40 by 40 centimeter cell, which is 5.5 pedestrians per square meter, which we were able to achieve such density in front of the bottleneck. I've seen a presentation from China where they let 2 streams of pedestrians going against each other, and they reached a density of 7 pedestrians per square meter. I can't. Even those 5.5 was quite like dense to me. So, okay, there is some ideas to do it. I'm quite surprised you don't have any comments, because usually everybody is pedestrian and everybody comes up with some idea how to modify it to make the model more realistic. So I have prepared an answer for such a question, so I will answer myself.
Someone asked them.
No, I just want to say that it is not very necessary to make the motion of the particles realistic, because you are not hopping between sides, walking rather continuously. So all the results you are looking at has to be zoomed out a little bit. So not watching the trajectories on the microscopic scale, but going somewhere to mesoscopic scale and watch it as a blurry crowd with some effects and phenomena which can be reproduced like that. But that's my opinion.
Okay, if there are no further questions, then let's thank again.